Today, we're going to talk about the photoelectric effect. Now, I know it might sound like some obscure topic from a physics textbook, but it's actually the secret behind how every single digital camera in the world works. So let's break down how this one idea literally changed everything. Okay, so take a look at all this gear. It's part of a pretty sophisticated solar-powered wireless camera system. You've got antennas, cameras, control boxes. I mean, it looks incredibly complex, right? But at its heart, all of this technology really just hinges on a single fundamental question. And that's the real magic, isn't it? How do you take something as, intangible as light hitting a sensor and turn it into the ones and zeros that make up a digital picture? Well, the answer to that question didn't just give us cameras. It sparked a revolution in physics. To find that answer, we actually have to go back in time, to a point where classical physics was hitting a major wall. See, physicists thought they had light all figured out, but a simple little experiment was about to prove them profoundly wrong. So here's the core of the conflict. Classical wave theory was simple. Light is a wave, and a bigger, brighter wave should have more energy. You can think of it like ocean waves. A giant tsunami has way more energy than a tiny ripple, right? Makes sense. But experiments showed something totally different. An incredibly bright red light couldn't knock a single electron loose from a piece of metal, but even a really dim violet light could do it instantly. The crucial factor wasn't brightness, it was color. Or, to be more precise, its frequency. And for physics at the time, this was a huge crisis. The solution required a complete paradigm shift. It meant we had to rethink the very nature of light itself. A new and pretty radical idea was about to change the game forever. And that revolutionary idea is the photoelectric effect. Now, the definition itself is pretty straightforward, but its implications are absolutely massive. This is the key process that turns light into electricity. So the really crucial point is this. Light doesn't just act like a continuous wave. It also acts like it's made of tiny, discrete packets of energy. Think of them as little bullets of light. And these bullets, these particles, are called photons. This whole idea that light is quantized became a cornerstone of the new quantum mechanics. And when you look at this, you can just feel the raw excitement of that breakthrough. This wasn't some polished theory handed down from on high. No, this was worked out in real time, in notebooks just like this one. You can almost see the equation taking shape, connecting the dots between light, energy, and matter. Now, to really get a handle on how this works, we're going to use a fantastic analogy, one that turns all this quantum physics stuff into something as simple as getting a paycheck. Believe it or not, it all boils down to this single elegant equation. This formula really does govern the entire interaction. On the left, you've got K max, which is the energy of the escaping electron. On the right, HF represents the energy of the incoming light packet, where F is its frequency, its color. And that energy has to overcome phi, which is basically a fixed cost to escape the metal. Okay, so here's how it all fits together with our analogy. Imagine an electron wants to buy its freedom from the surface of a metal. The incoming photon's energy, HF, is like its total income. It's the paycheck. But to get out, it has to pay a fixed tax. That's the work function, phi, and it's different for every metal. And whatever's left over, that becomes the electron's profit, its kinetic energy, K max. So income minus tax equals profit. It's really as simple as that. Okay, so now that we have our powerful little analogy, let's run through a few scenarios to see how this actually plays out in the real world. So what happens if the incoming photon just doesn't have enough energy? This is our first scenario where the photon's energy, HF, is less than that escape cost, phi. Using our analogy, this is like your paycheck being too small to cover your taxes. And it doesn't matter how many of these small paychecks you get, which is the same thing as making the light brighter, you can never afford the exit tax. So no electron escapes, no profit, no motion. All right, let's look at the break-even point. What do you think happens if the photon's energy exactly matches the work function? In this case, your income is just enough to cover the tax. You can pay the fee, and the electron is set free from the metal, but there's nothing left over. It has zero profit, which means it has zero kinetic energy. It's free, but it's not going anywhere. This minimum energy corresponds to what we call the threshold frequency. And now for the most interesting case, what happens when the photon comes in with more than enough energy to do the job? This is when your income is bigger than the tax. The electron pays the fee to escape, no problem, and the leftover energy becomes its spending money, It's profit. This profit is its kinetic energy, and it's what sends it flying off the metal's surface. And the more excess energy the photon had, the faster that electron moved. So, that's the theory. But how does this elegant little piece of quantum mechanics lead us all the way back to that high-tech camera we started with? Let's make the connection. Well, the sensor inside a digital camera, whether it's in your phone or in that big security system, is just a sophisticated grid of material that has been specifically chosen for its photoelectric properties. You can think of it as an array of millions of tiny electron traps, all just waiting for photons to arrive.
And this right here perfectly illustrates the whole journey from idea to reality. On the left, you've got the fundamental principle just sketched out with pen and paper. And on the right, you have its direct technological descendant, a software interface that uses that exact principle for things like motion detection. It's a straight line from a quantum idea to a practical tool we use every day.
So, here's the final payoff. When light from a scene enters the camera, each photon hits the sensor, and if it has enough energy, bam, it kicks an electron loose. This creates a tiny measurable electrical current. Millions of these events happening all over the sensor, some stronger, some weaker, depending on the light, are measured and stitched together by the camera's processor to build the final digital image. That's it. That's how light becomes data. So from a simple lab experiment to the phone in your pocket, the photoelectric effect is a perfect example of how a deep, kind of strange insight about the universe can become the foundation of our everyday technology. It really makes you wonder, doesn't it? What other quantum secrets are we already using, hiding in plain sight?